Okay, it's 5:30, so let's go ahead and get started today. Good evening, everybody. How's everybody doing today? How was the midterm? I guess the last time we were supposed to have a class session, we had the midterm. So I know there were some questions, and I know that there was the issue with problem 2, but hopefully that extra constraint helped people out on problem 2. Okay. So how's the midterm for everyone, first of all? Good? Good? Yeah. Yeah, it was a little bit long. I mean, I kind of made the assumption, as I was writing that you would have MATLAB to help you out. So, I kind of, took that into account with the midterm. So that's kind of the benefits of having a 24-hour exam like that, as you can have, a tool that really checks your work. So I haven't started grading them yet. So I anticipate I'll probably get to grading them tomorrow. So by Wednesday, you guys should have all the grades by then. So I know I'm a little bit behind grading stuff for this class, just because last week was pretty busy for me. But by Wednesday, I expect to be all caught up. Okay, so today we're actually going to be starting something completely new. Well, not completely new. I mean, it's still related to finite elements, but it's going to be quite a departure from everything that we've covered up to this point. And so what we're going to start this week is kind of what I kind of consider to be kind of the traditional kind of finite elements. And I think from here on, I think it'll be really interesting, just because what we're going to be doing is we're going to be building a theory that's actually behind a lot of the commercial codes like ANSYS and Abacus. Some of you might be familiar with too. Okay? And so what we covered up to this point was kind of more kind of just almost like an appetizer, I would say. And then what we're going to be covering from here on out is this is kind of more real traditional finite elements. Okay? But before we get started on that, are there just any questions I can answer? Okay. All right, so let's go ahead and get started. Okay. So just like I mentioned, finite elements, up to this point, we've kind of been solving, we haven't really been solving finite element problems, I guess, per se. What we've been solving really are just kind of structural mechanics problems or statics problems, but within kind of a finite element context. Okay. So I did this for a couple of reasons. So first of all, it's the textbooks kind of are a lot of them start with this kind of stuff. But second of all, what I really wanted to get you guys to get out of that first section of the course was kind of just the overall process of performing finite element analysis. Okay? And so things like forming the element stiffness matrices, assembling the global system, applying boundary conditions, and solving. So even though it's going to look like the stuff that we're going to be doing from here on out is a lot more math heavy or mathy, we're still going to be following that same process. So, we're going to be solving, very different problems than what we did before. So we're going to be solving basically differential equations now. But I want you guys to still remember that process that we covered in this first section of the course of element stiffness matrices, assembly, boundary conditions, and linear solution. Okay? But we're going to be transitioning a little bit. Because finite elements is way more than just kind of a tool to solve structural mechanics problems. It's actually a very versatile tool. Okay? And so to begin, I want to start with the definition of a boundary value problem. Okay. And so a boundary value problem, you might have heard this term previously in like a math class or something, but a boundary value problem is, usually it's used to describe the physical response or the physical, solution to any kind of a physical system. Okay. And so up to this point in the class, we've just covered one type of physical system, which was structural system. So we had, a structure that was made of trusses or beams or frames, and we solved for the solution, which was, the displacements or the rotations. Okay? And so finite elements can cover these kinds of problems, but it can also cover things like heat transfer problems, fluid mechanic problems, electromagnetics, resonance, frequency. It can do a lot of different things. And so kind of the all-encompassing terms for all of these kinds of problems physical problems is a boundary value problem. Okay? So a boundary value problem actually has two different parts, right? Or there, you can kind of think of it as two different ingredients to the recipe. Okay? And so the first ingredient for a boundary value problem is we call it the governing differential equation. And so if you think of like a lot of the really famous equations that you've covered in previous classes, like for heat transfer, we have the heat equation. For fluid mechanics, we have the Navier-Stokes equations, right? All of these are differential equations, okay? And so that's kind of the first ingredient, is that, you know, most physical systems that we know today, at least their physical behavior is governed by a differential equation. So, you know, one example that we'll cover today is for structural mechanics. Okay? Okay. And so we have this differential equation right here. So we have d dx of E times A times du dx plus b of x is equal to 0. Okay? And so this E right here, this is our Young's modulus, as it always has been. Okay? And this A right here is area. Okay? And the U that's in the differential here, U is the displacement. Okay? Okay. And so this b of x, this is kind of a new term right here, and we'll dive into this a lot more later, but this is a function that describes a body force. Okay? And so I want you guys to kind of shift your thinking a little bit from thinking of, you know, just purely structural problems to now we're kind of solving just more in general, just mathematical problems, which are governed by differential equations, okay? Okay, so that's the first part. And so the second part of a boundary value problem, you know, which kind of gives it its name, is the boundary conditions. Okay? So we already know what boundary conditions are. So boundary conditions basically describe the behavior of the system at the extremities of the domain. Okay? Okay. And so thinking back to kind of the structural problems we've been doing up to this point, these would be things like a fixed constraint, it would be things like a load or a force, okay? And so mathematically, it might look something like this, okay? And so if we wanted to apply, in this case, would be a Dirichlet boundary condition at u is equal to 0, okay? Okay. And so these are just examples. So these aren't just the only kind of boundary conditions that you would have, okay? And so you would have, you know, another type of boundary condition that we can have is a boundary condition on the derivative, okay? And what we'll see, you know, as we do the examples today, is that a boundary condition on the derivative is kind of the same thing as a force boundary conditions, okay? And so if we connect this to the types of boundary conditions that we covered before, so the top one here, because it's a direct boundary condition or direct constraint on the displacement, this would be like a Dirichlet boundary condition, so we'll call that D, okay? And then the second type of boundary condition here, because it's a boundary condition on, you know, a derivative, it's not directly onto the, it's not a direct boundary condition onto the displacement itself. We'll call this a Neumann boundary condition, so the N, okay? Okay. And so I drew this kind of, you know, distinction between the two because, you know, I don't want you to kind of think of these two things as kind of just, you know, two separate things. You know, they're all part of the same problem, but they're kind of responsible for two different parts of your domain, okay? And so if you think of your domain as kind of a, we'll kind of just draw a potato here, or a blob. It's an awkward looking potato, okay? There's kind of two parts of this domain, right? And so there's the interior of the domain, right, which I've kind of highlighted in red. And so the interior of the domain is kind of one part. And the second part of the domain is the boundaries or the extremities of the domain. Okay? And so the governing differential equation, what this is responsible for is describing the behavior on the interior. Okay? Okay? Whereas the boundary conditions are responsible for defining the behavior at the boundaries. Okay. All right. And so what we're going to do today is we're going to talk about we're going to go into a specific example of boundary value problem. What this means for finite elements and how we can move forward with this. Okay. Okay. Are there any questions on this? Okay. Okay. So let's do an example of a one-dimensional boundary value problem. Okay. And the example that we're going to do is elasticity. Okay. And so this is kind of the boundary value problem for elasticity problems. Okay. In particular, we're going to go over what's called the strong form of this boundary value problem. And so I'll go over kind of what that means later. So, for every boundary value problem, we can kind of represent it in two different ways. So we're going to go over the strong form, because the strong form is kind of more traditional of how, it's usually presented in other textbooks and other classes. But then later on, we're going to cover what's called the weak form. Okay? And the weak form is actually going to be that's going to actually form the basis for our finite element solutions. Okay, so let's start with the strong form first. Okay? And so for elasticity problems, we have something that looks like this. So let's say that we have just a truss element. Okay? So let's say that it's fixed on the wall on the right-hand side here. Okay? And so our truss element might look like this. Okay? And so along our truss element, let's say that we have a body force that's being applied. Okay? Okay. This truss element has a length L. Okay. And in particular, we're going to define the x coordinate to be in this direction, going from the left to the right. And it starts at over here. And so this point right here is going to be x equals 0. Okay. And then in addition to this, we're going to apply a stress on this side. Okay. And so this will be T bar, and this will be some applied stress. Okay. Okay. And so there's some other properties that we have to keep track of for this truss. Okay. And so if you remember from kind of the first part of the class, a truss element has two other properties that's important. So first we have the Young's modulus. Okay. Notice how I made this Young's modulus a function of x. And so we're no longer assuming that the Young's modulus is constant. So now we're accounting for the fact that the Young's modulus can change throughout the length of the truss element. Okay. Okay. And then same thing for the area. So A of x right here represents the cross-sectional area of the truss element. Okay. And so what we're interested in solving for in this problem, very similar to what we did in the first part, is we're interested in solving for the displacements of this truss bar. Okay? But we're not just interested in solving for the displacements at discrete nodes. What we want is kind of what's called a spatial distribution of displacement along the truss. In other words, we want to solve for the function u of x. Okay. Okay. And then one other small thing is that this body force right here has units of force over length, so it kind of has the same units as a spring constant. Okay. Okay. And so the way that we're going to do this is the first thing we're going to do is we're going to form our boundary value problem for this truss. Okay. Okay. So in other words, we need to find out what's the governing differential equation and what can we use for the boundary conditions. Okay. All right. So the question is this like D'Alembert's principle in nature? Not really. So it's D'Alembert's principle. I think is something a little bit different. So basically, we're just going to be deriving the differential equation basically from first principles, basically. We're going to do a very shortened version of it because this is not a statics class or a structural mechanics class. We just want to get to the differential equation. Yeah. All right. Are there any questions on this? Okay. Okay. So our goal here is we want to formulate a differential equation and the boundary conditions. So the boundary conditions, we've kind of seen those before. So I'm, we'll get to that a bit later. But first, let's form the differential equation. Okay. And so to do that, let's cut out a small slice from our truss bar and then perform a force balance. Okay. And so let me redraw our truss bar like this. Okay. So we have our tension over here, or our traction. Right, and so what I'm going to do is I'm just going to cut out just a small slice of this truss. Okay. Oh, we also can't forget that we have our body force that's going to be all throughout the truss, just like this. Okay, so let's take this kind of tiny this tiny portion right here and kind of blow it up. Okay, and then now let's perform a force balance. Right? So first, let's define kind of the geometry of this. So let's say that this this little tiny slice has a length of dx. Okay, and we'll define this this part right here to be coordinate x. Okay, and so the x coordinate of the right side of this guy will be x plus dx. Okay. Okay. And so inside this tiny element, we have our body force. Okay. And so what we're going to do for our body force is we're going to evaluate that at the midpoint of our tiny tiny slice right here. Okay. Okay. And so this b at x plus dx over 2, this is simply just the body force evaluated at the midpoint. Okay. That's why we have the x plus dx over 2. And so one other force that we need to take into account here is that since we kind of know this from before, that whenever you apply a force onto a truss bar, there are going to be some internal stresses that develop within the bar, right? So that you solve for that in the midterm, and we solve for that kind of in the first part of the class, okay? And so we need to represent that into our little tiny slice right here. Okay. And so let's define a function n right here, where n right here, this is the what's called the normal force. Okay. So this is an internal force. And so this is a force that's felt on the interior of this truss. And that's basically just to make sure that this tiny slice right here stays in static equilibrium, right? And so, if we say that our entire truss right here is in static equilibrium, then every small slice of it also has to be in static equilibrium. Okay? And so what we're going to do is we're going to take this tiny truss to this tiny slice right here and sum up all the forces and set it equal to 0. Okay, so let's go ahead and do that. Okay. And so if we sum all the forces, let's start with n of x right here. So since n of x is pointing to the left, we're going to have a minus n of x. Okay. Plus, we're going to have our n of x plus dx, which is the internal normal force on the right. And so that's going to be n of x plus dx. Okay. And then to that, we're going to add our contribution from the body force. So we're going to have plus b of x plus dx over 2. Okay. But since this is a body force, remember the body force has the units of force over length. And so in order to get the actual force from this body force here, we need to multiply this b by dx. Okay. Right. And so by multiplying by dx, we get a force from the body force. And so this is kind of the equation that we get just from summing up the forces for this tiny slice of truss. Okay. All right. Are there any questions on this? Okay. Okay. And so what we're going to do at this point is that now that we have this kind of algebraic-ish equation, we need to turn this into a differential equation. Okay. And so let's take that entire equation and let's divide by dx. Okay. Okay. And so we have n at x plus dx minus n of x all divided by dx, okay, plus b of x plus dx over 2, okay, equals 0, right? And so you can see here we're getting close to something that looks like a differential equation, right? Because we have a difference of 2 n's over dx. And so, if you remember from from your first calculus class, the way that we can actually get a real derivative of this is we can take the limit as dx goes to 0. Okay. And we do that, we're left with the following equation. Okay, so we have the first derivative of the normal force, of the internal normal force, dn dx, plus b of x is equal to 0. Okay. And so what we've arrived at here is a differential equation that describes the static equilibrium in the B. Okay. And in this case, it's an ordinary differential equation because we only have one independent variable. Okay. All right, so we gotten what we sought to do. So we wanted to get a differential equation that describes the behavior within this truss. But right now in this form, it's not really that convenient, right? Because what's our primary variable here? So our primary variable is n, right? And so when we actually solve this differential equation, we would be solving for the internal force n. And so a lot of times this is not that convenient. And the main reason it's not that convenient is once we have to start applying boundary conditions, you know, it's hard to apply the boundary conditions on n because that's not usually clear just by looking at a structure. Okay. And so let's work on this a little bit more just so that we can obtain a differential equation in terms of displacement. Okay. So displacement is really nice because, you know, a lot of our boundary conditions are, you know, in terms of displacement, right? Okay, so let's work on this a bit. So let's write another expression for the internal stress or the internal force. Okay. Okay. And so one way that we can rewrite internal force is we can say that it's the product of the internal stress multiplied by the area. Okay, so this sigma of x right here, this is internal stress. Okay. And this a of x right here, this is cross-sectional area. Whenever I see internal stress and I think of, you know, how stressful it is to be as a student, you know, whenever I internal stress, I'm like, me too. Right? Okay. And so let's take this expression here and let's plug that in for n up above, but with one more caveat. So we need to write the stress in terms of something else. Okay? But before we do that, are there any questions on this? Okay. Okay. And so if we plug this in for n. This is our differential equation right here. So we have d dx, okay, of n, but now n is equal to a of x sigma of x plus b of x equals 0. Okay, but we're not quite there yet because this is not yet in terms of displacement. Okay, in particular, we can put this stress term in terms of something that's a little bit more convenient. Okay, so if we invoke kind of linear elastostatics here, we can say that the stress in an object is equal to the product of the Young's modulus multiplied by the strain. Okay? In particular, the strain we can write in terms of the displacement. Okay, and so all I did to go from this term to this one term was I substituted epsilon of x. I substituted in du dx, where u is our displacement. Okay. And so with that substitution, so if we plug this guy in for sigma of x, then we're going to have our differential equation in terms of u. Okay, so let's go ahead and do that. So we have d dx of a of x, e of x. Okay. Remember, we haven't made any assumption on the area or the Young's modulus, so those can vary with x. Okay. Du dx plus b of x is equal to 0. And I'm going to box this guy because this is our differential equation here that solves for the displacements in this truss. Okay. Right. And going off what we talked about at the very beginning of class today, what this differential represents is it can be solved for the solution on the interior of your truss. Okay. All right, question. Yep. Okay, so that's part one of our boundary value problem, right? So now we have a differential equation which describes this, right? So we're gonna actually be solving problems like this. So you know, dust off your old ODE stuff. Right? But the last thing that we need to do is we need to address the boundary conditions. Okay. And so just like we saw before, we're going to have Dirichlet and Neumann boundary conditions, but they're going to take on a little bit of a different meaning. So in this particular case, they're going to mean the exact same thing. So a Neumann boundary condition will be our forces or stresses, and Dirichlet will just be our constraints. But I want you to kind of think of these definitions as a little bit more broad, especially once we get into heat transfer on Wednesday. Okay, so first let's actually write out what our boundary conditions were for this case. Okay, so if we go back to our original drawing, okay, in the purple right here we have an applied stress on the left-hand side, okay, and then our other boundary condition, which I didn't write in, was that our truss was fixed on the right-hand side because it's kind of cemented to the wall. Right? Okay, and so let's kind of write those down again. So first we have a traction or a stress. Okay, so a traction is nothing more than a force over area. Okay. Okay. And then our second boundary condition will be a fixed boundary condition on the right. Okay. Okay. And so let's go ahead and go over kind of a similar a similar derivation, although not nearly as long, for these two types of boundary conditions. But before I do that, are there any questions on this? Okay. Okay, so let's do let's take a look at the force balance with the traction boundary condition on the left. Okay. Oops. All right, so let me draw kind of a tiny slice of the truss right here. Okay. And then in purple, we're going to do our traction. Okay. Remember, a traction is nothing more than a force over area. And so the other thing that we're going to need here is we're going to need the cross-sectional area here. Right? And so since this is at the boundary of our domain, we actually know the x-coordinate. So we're going to say that this is going to be a at x is equal to 0. So we'll just call it a of 0. And so just like we did on the other one, we also have our body force. Okay. Right. And so this is going to be b at dx over 2. Okay. Because the length of this is going to be dx. And then opposing this this traction on the interior of our domain is going to be a normal force. Okay. And so particular, it's going to be the internal normal force at n is equal to 0. Okay. Okay. So just like we did before, let's sum up all the forces. Okay. And then what we get is the following. So in order to get a force from this traction, what we're going to do is we're going to multiply the traction by the area. Okay. Okay, so we can have traction times a of 0. Okay. And so that's going to the right, so that's positive. Okay. And then we're going to add our internal normal force, so we can have plus n of 0. Okay. And then we're also going to add our body force, b of dx over 2 times dx. Okay. And all of this is equal to 0. Okay, and so in this particular case, what we're going to do next is we're just going to simply take the limit as dx goes to 0. Okay, and so by doing that, we're going to cancel out our body force term. Right? And so all that we're left with is this. Okay? And so what we're left is t bar times a of 0 plus n of 0 is equal to 0. And so let's plug in for n is equal for n here. Okay. Okay. Because from the previous derivation, we know an expression for n in terms of the displacements. Okay. And so let's say that n of 0 is going to be equal to e of 0, a of 0, and du dx at 0. Okay. And so we plug that in, we get T bar A of 0 plus E of 0, A of 0, du dx at x is equal to 0. Okay, all this is equal to 0. All right. And so if we cancel out the A of 0, because both terms have that A, then what we arrive at is our boundary condition. Okay? And so what this tells us is that E, the product of E times du dx at x is equal to 0, this is equal to minus T bar. Okay. Right? And so in other words, with the traction boundary condition, we have a boundary condition based on the derivative of our solution. Okay. Okay. And so these types of boundary conditions, which is what we've been calling them before, but we can give it kind of a more precise and kind of more general definition here. So any type of boundary condition that places a condition on the derivative, we call these Neumann boundary conditions. And so what you'll see is that when we do heat transfer problems, we'll have boundary conditions that are based on the heat flux. And the heat flux is simply equal to some constant multiplied by the derivative of the temperature. Okay, and so very similar to that, or very similar to this, those will be considered Neumann boundary conditions. Okay? And so, and also just for the sake of completeness, especially, just kind of a heads up, we're kind of switching textbooks at this point. So we're moving from the first textbook to the other one. Okay, and so in that textbook, you'll see that textbook describe these as natural boundary conditions. So Neumann boundary conditions, natural boundary conditions, it means the same thing. Okay, so they both start with N. Okay, right. And so again, just to kind of reiterate, any boundary condition that places a constraint on the derivative of our function, in this case is du dx, those are considered our Neumann or natural boundary conditions. Okay. All right. Any questions on this page before I turn the page? Okay. Okay, so that's Neumann boundary condition. So now let's go over the fixed boundary condition. Okay. Okay. And so our fixed boundary condition here is pretty simple. So it's just going to be u of L is equal to 0. And so what that says is that when x is equal to L, then our displacement has to go to 0. Okay. Okay. And so in these particular case, what we can see here is we're directly specifying the value of our solution. Okay. So we're not dealing with any kind of derivatives or anything. We're just saying that the displacement, which is our solution variable, has to be 0 over there. Okay. And so in these particular cases, when we directly specify our solution variable, these are called Dirichlet boundary conditions. And so just like the Neumann boundary conditions, you might see different terminology, based on whatever textbook that you're reading. And these are often called essential boundary conditions. Okay. Okay. And so I want to make one quick note before we move on, just because we've done the only Dirichlet boundary conditions we've seen so far are just kind of fixed constraints, but that's not the only Dirichlet boundary condition that we can have. Okay? And so a lot of times you want to set a Dirichlet boundary condition to be a value that's not 0. Okay? And so I'll just make a quick note that the value of the Dirichlet boundary condition does not have to be 0. It just so happens that when we're doing structural problems, most of the time, an essential boundary condition for a structural problem just happens to be 0, just because it's a constraint. Okay. Okay. And so now that we have the differential equation, we have the boundary conditions, we're ready to state the strong form for our boundary value problem. Okay. And so remember, a boundary value problem, at least in the strong form, has two ingredients. And so first thing will be the differential equation. Okay, so let's go ahead and write that out. Okay. And so our differential equation given by this. Okay. Okay. Okay, so we have d dx of EA du dx plus b of x equals 0. Okay. And then the other thing that's customary is to specify where in the domain does this equation take place, okay? Or where does this hold? Okay. Right, so let me write in a different color just to kind of emphasize that. Okay. And so this differential equation right here, remember, this describes the solution on the interior of our domain. Okay. Okay. And so in this case, our domain, which is just a one-dimensional thing from x equal to 0 to x equal to L, okay? The interior of this will be given by this inequality here, where 0 is less than x, which is less than L. Okay. Right? And then in addition to that, we have our boundary conditions. Okay? So we have E du dx, okay, at x is equal to 0. Okay? And this is equal to minus t. Okay? And then the location in the domain where this is specified is x is equal to 0. And then the last boundary condition, which is our Dirichlet one, we say that u of L is equal to 0, and then the part of the domain that this specifies is at u is equal to L. Okay. And so here's our full boundary statement of the boundary value problem for this truss bar. Okay. All right, any questions on this? Okay. So let's do just a really quick example just to show you, how you can solve for these problems. Because in 1D problems, we're usually blessed just because there's only one independent variable. And so a lot of times you can actually solve for this solution. Okay? So let's consider the following structure. So let's say that we have a truss. Okay? And so let's say that it's fixed on the right-hand side. And then we also have a stress here of 100 Pascal. Let's say that the Young's modulus here is a constant, and we'll say that's equal to 100 kilopascals, 100 kPa. And the area here is just going to be simply 0.1 meters squared. Okay? Okay. And so in this problem, let's solve our boundary value problem for the displacement. Okay? Okay. Okay. And so let's take our boundary value problem from before, and then let's start to solve the differential equation. Oh, we have also no body force here. Okay. Okay, so let's start with our differential equation. And so, the boundary value problem that we derived previously, that's kind of the most general case. And so let's start applying some simplifications here based on this problem. Okay? And so first of all, let's apply the fact that we have no body force. Okay. Okay. And so if we have no body force, then the b of x is equal to 0. Okay. And then let's also apply the fact that our Young's modulus and our area here are constants. So let's pull them out of the differential. Okay. Okay. And so we apply these simplifications. What we get is E times A times d squared u. Okay. So now we have a second derivative, dx squared, because we apply this d dx onto the interior. So now we have, d squared u dx squared is equal to 0. Okay. Right. And so since this whole thing is equal to 0, we can go ahead and cancel out E times A, because we can just divide both sides by that. And then what we're left with is just d squared u is equal to 0. Okay. Right, so we have a very simple differential equation here. So we don't need to apply any kind of characteristic equation, solve roots, or any kind of that stuff. And so what we can do simply here is we can just simply integrate this twice in order to find the solution. Okay. And so let's integrate once. Okay. So we integrate once. On the left-hand side, we're left with du dx. Okay. And so the integral, what's the integral of 0? And so normally the integral of 0 is just 0, but since we're doing indefinite integrals here, we have to add a constant. Okay. And so this c1 right here is an arbitrary constant, just because we can't solve for it just yet. Okay. And so let's integrate this again. Okay. And so by integrating the left-hand side, we simply get u of x, which is what we want. Okay. Next, we're going to integrate c1, where c1 is just a constant. So integral of a constant is just c1 times x. Okay. And then next, we're going to add another constant there, c2. Okay. All right. And again, that c2 appears just because we're doing a indefinite integral of our equation. Okay. I'm gonna turn on the lights because my eyes are straining right now. But if there's any questions, go ahead and type them in the chat. All right, sorry about that. Okay. Are there any questions on this? Okay. And so now that we've reached this form of the solution, what we need to do here is apply our boundary conditions. Okay. Okay. And so let's start with the boundary condition on the left-hand side. Okay. And so this, this situation right here is different from our example, because remember our example was fixed on the right-hand side. So since this is fixed on the left-hand side, this is where we're going to apply our Dirichlet boundary condition. Okay. And so at x is equal to 0, we just have simply u of x is equal to 0 is equal to 0. Okay. And so now let's apply this boundary condition to solve for one of the constants in our previous expression. Okay. Okay. So we do u of x is equal to 0. Okay. Is equal to 0, and we plug in 0 into our expression. So we have c1 plus c1 times 0 plus c2. Okay. And so what this tells us is that c2 is equal to 0. Okay. And so in order to satisfy this boundary condition, our c2 here has to be 0. Okay. Okay. And so now let's apply our other boundary condition. Okay. And so our other boundary condition at x is equal to L, okay, is simply going to be the following. Okay. And so at x equal to L, we have our Neumann boundary condition. So we have E times du dx. Okay. Okay. And this is at x equal to L. And this is equal to, in this case, it's going to be a positive 100 pascals. Okay. And so the reason I chose 100 pascals here is because this stress that we're applying on the right is tensile in nature, right? So it's we're pulling the bar apart, and so that's opposite of the previous example which was a compressive force. Okay, and so you have to be kind of careful with your signs here to make sure that you use the correct signs. Right? Positive because tensile. Okay. And so if we plug in for this, okay, and so we plug in for E first. So E is simply just going to be a constant. So then E was 100 kilopascals. Okay. And so 100 kilopascals is going to be 100,000 pascals. Okay. Du dx, if we go by off this solution right here, okay, so du dx is simply just going to be C1. Okay. And all this is equal to 100 pascals. Okay. So this tells us that C1 is equal to 0.0 0, 0, 1. Okay. And so that gives us our two constants. And so finally, we can say that u of x is equal to 0.001 times x. Okay. So this simple, just ODE stuff. So strong form, usually is the first thing that's presented because this is kind of the way that you're presented with problems, when you're learning these for the first time. All right. Are there any questions on this? Okay, so that's the strong form of the problem. So strong form boundary value problems, again, this is traditionally kind of what's taught in a lot of classes. And, if you've taken like an engineering mathematics course, you probably learned a lot of techniques for solving these kinds of ODEs. Okay? And so now we're going to bring in kind of the twist that that's kind of required for finite elements, and that's the weak form. So I'm going to shorten boundary value problems for BV as BVP. Okay, so BVP just stands for boundary value problems. Right? Okay. And so just like the name implies, this is just another form of the boundary value problems. Okay. But I want you to kind of guard against kind of your first kind of gut impression by reading this. So just because we call it the weak form doesn't mean that it's worse than the strong form. Okay. And so actually, I'm going to present to you a different form of these equations, but it's actually going to be equivalent. So whether you solve the strong form, weak form of the problems, you're going to get the same answer because it's the same problem. It's just presented in a different way. Okay. And the reason we go this route is because the finite element formulations are actually based off this weak form. Okay. And so the reason it has the name weak, I'll kind of save that for a little bit later. Because I think it makes a bit more sense, in context. But I just want you guys to always remember, so the weak form does not mean inferior. Okay, weak form just means that it's, it has kind of a mathematical meaning to it. So I'll admit that it's a pretty poor name for this kind of thing because whenever people hear weak form, they think, oh, this is the sucky form. So it's not the sucky form. It's totally fine. It's just a different name for it. Okay. Right, so it's a weak convergence or weak continuity. So that's kind of what it means. But we'll get into that a little bit. Okay. Okay. And so the starting point for the weak form from a boundary value problem is that we're going to take our differential equation from the strong form and actually multiply it by an arbitrary function. Okay. Okay, and so I'm going to take kind of our previous example as as this case, but this process can be applied for anything. And on Wednesday we're going to do this for heat transfer as well. Okay, and so we're going to start with our differential equation. Okay, so our differential equation in this case was d dx of EA times du dx, okay, plus v of x. Okay, is equal to 0. Okay, so that was our strong form differential equation. And then what we're going to do here is we're going to multiply by an arbitrary function, and we'll call it w of x. Okay. And so this might seem, extremely strange at this point because, you're probably your first impression when seeing this is like, why the hell would he do that? Why would we do this? And why would we say that it's an arbitrary function? Because arbitrary means it can be anything, right? And so at this point, it really can be anything. Okay? And so, I think it's really fair to ask at this point. So what is W of X? You know, what is the requirements on it? And you know, how is this going to help us? Okay. And so, you know, all those questions will be answered in you know, throughout the lecture today. But, you know, I do want to say one requirement for W of X. Okay. Right. So the requirement that I'm going to specify is that it has to disappear at the locations of our essential boundary conditions or our Dirichlet boundary conditions. And so anywhere that we have a Dirichlet boundary condition on U, you know, W has to be equal to 0 there. Okay. Okay. And so kind of one way that you kind of specify this, you know, generally is we can say that U at gamma U, okay, is equal to U naught. Okay. And so I've used this symbol gamma U here. So this is the this is kind of the general form right here for Dirichlet boundaries. Okay. Or in other words, these are the locations where we're applying a Dirichlet boundary condition. Okay. And so at those same locations, we're going to require that W, our function W, is going to be equal to 0 there. Okay. So right now, this is our only requirement on W, is that whenever we have a Dirichlet boundary condition, our W has to be 0 at those places. Okay. And it's different. So remember, for U, we can say that the Dirichlet boundary condition can be anything, but for W, at the Dirichlet boundary condition, it has to be 0. Okay. Okay. Any questions on this so far? Okay. Okay. And so now that we've multiplied by this strange function W, we're going to do another really strange thing, is we're going to integrate this over the domain. Okay. So, you know, it's really fair to ask, you know, why the heck are we doing all these things? Right? And I'll tell you kind of a story for when I first took finite elements. So I first took finite elements from a professor, which was this like really big and intimidating Latvian guy. So he has kind of a reputation in the department for being kind of very intimidating and very strong-willed. Okay, and so you know, we were going through this derivation for the weak form, and then you know, someone asked, said, "Why are we doing all these things?" And then he just basically looked him straight in the eye and says, "Because I told you to." And I can't really imitate it because I'm not a very intimidating kind of guy, but you know, once he said that, then the whole class kind of just shut up for the rest of the lecture. So, but you know, it's very fair for you guys to be asking that, and in fact, you guys should be asking, you know, why are we doing all these steps? But it'll all be clear, trust me. Okay. And so what I've written here is the integral of our you know, of our expression from 0 to L. Okay. And then I've included this kind of extra little caveat right here. Okay. And this kind of describes our requirement on W. Okay. And so if you've never seen this symbol right here, and so what this symbol basically is kind of short for is for all. Okay. And so what this requirement says that, you know, we have the integral of Wx times d dx of e times a du dx plus b of x, dx is equal to 0. Okay. And then our requirement on W is that for all functions W of x, W at our Dirichlet boundary has to be equal to 0. Okay. And so all that is basically just stating our requirement here. Okay. And so what I'm going to do at this point is I'm going to separate it into two integrals. So we have an integral on our derivative, and then we also have our integral on our body force. Okay. And so first we have this integral right here. Okay. So we have integral from 0 to L of W of x d dx of E A du dx, okay, dx, right? And so that's just this first term up in our expression here, plus integral from 0 to L of w of x, b of x dx, okay? And this is equal to 0, okay? And so all I did was I just split up the two integrals so that we can kind of work on them individually, okay? Or it's more like we're only going to work on just the first one. Okay. And so let's go ahead and do that. Okay. And so we're going to work on the on this first term right here. Okay. And so one thing I want you guys to notice on this first term is that we basically have two functions of x, ignoring e and a. So e and a are just properties, so they're kind of just along for the ride. But in terms of just functions, we have a w of x and we have a u of x. Okay. And so what I want you to kind of notice about this is I want you to count the derivatives on each of w of x and u of x. Okay. And so let's start with u of x. And so u of x, you can see right here, first we have this derivative, right? Okay. And so that's one derivative on that, okay? And then we also have this derivative over here, okay? And so that's kind of the outer derivative. So for u of x here, we actually have two derivatives. Okay. And then let's look at w of x. Okay. And so, let's count the derivatives on w of x, okay? And so you can see here, just like the fact, matching the same number of championships that the Clippers have, w of x has 0 derivatives here, okay? Okay. And so, w of x is kind of looking at this and saying, hey, that's not fair. How come you have two derivatives and I only have, how come you have two derivatives and I have 0, okay? And so, obviously, this is not, Lakers aren't going to give any of their 17 championships to the Clippers, but, because this is finite elements, we can do a little bit of sharing right here, okay? And so what we're going to do is we're going to manipulate this, this mathematical expression here to kind of what we call balance out the derivatives, okay? And the way we're going to do that is we're going to use, maybe if an old friend that you haven't seen in a while, is we're going to use integration by parts. Roasting the Clippers never gets old. All right, any questions on this before we do our integration by parts? Okay, so let's go ahead and do that on the next page. Okay, and so let me rewrite our integral here just so that we can kind of see it. Okay, and so we're going to use integration by parts here to kind of balance out the derivatives. Okay? And so I don't even know how integration by parts are taught nowadays, but this is kind of the way that I learned how to do it. Okay, and so I start by defining two different quantities. So I'm going to start with u. Okay, I'm going to start with dv. Right, and we need to separate our integral expression here into these two terms. Okay, and so for u, I'm going to define that to be w of x. And for dv, I'm going to have this to be the rest of it. So dv is going to be d dx of EA du dx. Okay? And so what we're going to do from here is we're going to compute, on the u side, we're going to compute the derivative of this. So we're going to have dv. Okay? And so the derivative of this is going to be dw dx. Okay? So we're just going to simply take the derivative. And then on the v side, oh, sorry, this is du. And then on the v side, we're going to take the integral of this, okay? And so by taking the integral, that's going to be simply just going to cancel out this derivative out in front. And so we have e times a times du dx. Okay. Okay. And then once we've formed these expressions right here, what we're going to do is we're going to go diagonally down this way, okay, and take the product of u times v, okay, and then we're going to subtract the integral of v du. Okay. So this is how I've learned how to do integration by parts. But you know, if you're familiar with kind of a different way, you know, I've known kind of the table way, and so perform integration by parts, you know, however you feel most comfortable. But you know, as long as you kind of get this result that we're going to talk about right here. Okay. Okay. And so let's go ahead and do that. Okay. So first we have u times v, and so u times v is going to be w of x e times a du dx. Okay. And since this is an integral, we're going to evaluate this from 0 to L. Okay. Right. And so we basically consider that term to be already integrated. Okay. And then we're going to subtract this integral right here. So we're going to take integral of v. And so v in this case is ea du dx. And then multiplied by du, and du in this case is dw dx. I think I missed a couple. I think there should be a dx here and a dx right there, something like that. Okay. Right. And so let's look at this result here. So from this result, you can see that we started with an integral up here where the derivatives were unbalanced, right? We had one term with two derivatives and one term with 0. Okay. And then what we ended up with is now an integral expression where the derivatives are balanced. Okay. Okay. So perfectly balanced, you know, as all things should be, right? Okay. But you know, the price of getting this perfectly balanced derivatives is we have this kind of extra guy right here. Okay. And this extra guy is a little bit weird. So let's actually evaluate this. Okay. Okay. And so since this term is technically already integrated, we can go ahead and just plug in our bounds here. Okay. So we have one bound at x is equal to 0 and one bound at x equal to L. Okay. And so we're going to have w of L times ea du dx at x is equal to L, okay, minus w of 0 ea du dx at x is equal to L. 0. Okay. Okay. All right. So that's the so that's kind of the expression for that term right there. Okay. Okay. And so what I've highlighted in green right there are, you know, w of L and w of 0. And so this is just kind of just plain w evaluated at one of the boundaries. Okay, so one of them is going to be at the left-hand side at w is equal to 0, and then or x equal to 0, and one's going to be on the right-hand side at x is equal to L. Okay. And so at this point, you know, what I want you to remember is one of the requirements on w. Okay. Okay. Remember, what we required for w is that w has to disappear at one of our essential boundaries, okay, or our Dirichlet boundaries. Okay. And the requirement for any kind of boundary value problem is that you have to have one essential boundary. You have to have at least one Dirichlet boundary. And so remember, for all the finite element problems that we did in the first half of the class, there's always at least one constraint there that was kind of constraining the whole thing. Okay? And so what that means is that one of these two terms that we have on the bottom here, one of these guys just has to disappear because, you know, one of these has to be a Dirichlet boundary. Okay? And so for this, you know, we haven't defined what our Dirichlet boundary is for this problem, but let's just assume that x is equal to L is a Dirichlet boundary. Okay. And so if x is equal to L is a Dirichlet boundary, then what we have is W of L equal to 0. Okay. And if W of L is equal to 0, then that totally cancels out that first term right there. Okay. All right. And then this second term right here, actually we can work on it a little bit more, but this page is getting a little bit messy, so I think I'm going to do it on the next page. So before I turn the page, are there any questions on this page right here? Okay. Okay. And so now let's write out our other term. Okay. And so that's the other part of our expression right there. Okay. In particular, what I want to focus on are kind of the terms that I've highlighted in orange right here. Okay. And so if you go back to like one of the beginning slides that we had, okay. Let me see. Let's go to this one. Okay. And so what you can see from this slide is that this product of E times du dx is equal to our Neumann boundary condition. Okay. And so that's not a coincidence. And so what we have right there is in this expression right here is E times du dx at one of the boundaries. Okay. And so if this place is not a Dirichlet boundary condition, then this has to be a Neumann boundary condition. Okay. And so for a Neumann boundary condition, let's make the following assumption. Okay. And so let's say that let's say that we have E times du dx at x is equal to 0. Okay. Let's say that we know that it's a compressive force in this case, and that's so this is going to be equal to minus t. And so, you know, for this weak form derivation, I'm obviously making an assumption for the problem, but you know, for other problems where you have either a tensile boundary condition or not, or it's on the other side, you know, you have to make that as adjustments. And so, you know, what I did on the previous page where I assumed that W of L is equal to 0, and I assume here that we have a compressive boundary condition at the beginning. You know, this in particular, these conditions match our derivation for the strong form. But you know, if you're looking up the weak form for just kind of a general problem, you know, you have to make sure that you assign these carefully. Okay. And so if we plug that in, basically what this is you know, W of 0 times A of 0 times T bar. Okay. Okay. So that was a lot of kind of you know, integration and filling in terms and making assumptions. So let's kind of pull it all back together. Okay? And so if we put this all back together, we get the following expression. And so first we have this guy. So we're going to have W of 0, A of 0, T bar, okay, minus our balanced derivative guy right here. Okay. And so this is going to be integral from 0 to L of dw dx times E times A du dx, okay, dx, okay, plus our body force term. And so we pulled this guy out at the beginning and we kind of just forgot about it, okay? But we got to bring him back here. So integral of 0 to L of Wx, B of x, okay, dx, and all this is equal to 0, okay? And then we also have to state our requirements on W, okay? So this is for all W where W at gamma U is equal to 0, right? In this case, our gamma U is equal to L, okay? And so for this particular problem, we say that, W of L, which is our Dirichlet boundary condition, is equal to 0. Okay? And this, what I have boxed right here, is the weak form of our boundary value problem. Okay? And so we're out of time, but I want to just make one observation about this weak form, is that because of the way that we define W and because of the integration, our boundary conditions are all baked into the same expression, right? So it's different from the strong form. For the strong form, remember, we had a differential equation, and then we had our two boundary conditions that were kind of separate. But in the weak form, one of the nice things is that our boundary conditions are just kind of baked right in. So we just have one equation. Granted that we know some of the conditions on our W, but besides that, everything else is kind of baked exactly into this expression. Okay. Okay, so on Wednesday, what we're going to do is I'm going to talk about kind of the nice things about this, and then we're going to go through this process for heat transfer simulations at all. Okay. Okay, so that's all we got time for today. So thank you everyone for tuning in. So I'll stick around if you have any more questions, but if not, have a great evening, and I'll see you on Wednesday.
Professor, I have a question.
Sure, what's up?
Could you back to the page 8?
Page 8, sure.
Yeah. Yes, for x equal to 0 and x equal to L, that's our boundary condition, that's right?
Correct, yes.
And could you go the next page to your example?
Mm-hmm.
When we apply the boundary condition, I think that is the next page after this.
Yes.
When I see that x equal to 0, the u of x0 is equal to 0. That's right?
Yes. Mm-hmm.
But in the page 8, the x equal to L, when x equal to L, the u is 0.
Yeah. So the example that we did for the derivation, remember I said it was an example. So this is kind of the problem that we did. So this is different than the example that we did, right? So in this case, the fixed boundary condition was on the right-hand side, okay?
Mm-hmm.
And so that's why for this derivation we said that u of L is equal to 0 because that's where the fixed condition was. But for this other example right here, the second example, our fixed boundary condition was on the left-hand side right now.
Okay, that means that depends on which side of the truss is fixed and which one is not.
Exactly,
and
right.
The place that is fixed is our first, that means the x equal to 0. That's right. And the other side is x equal to L.
Yes, correct. Yeah. Mm-hmm.
Thank you very much.
Yep. All right, Stephen, so your question was, what's the reasoning behind the W of X in the weak form? Yeah, that's a great question. And so, I'll get into this kind of much more on Wednesday, but, it's a little bit kind of I've kind of read into this a lot too, because it is kind of strange. But the whole point of the W is actually just to get this. Okay? So this thing right here, where the derivatives are balanced, this is actually something that's really, really nice for finite elements. Okay, and it has less to do with the fact that the derivatives are balanced. It's more the fact that now the highest order derivative in our expression is just 1, right? And so in our strong form expression right here, you can see that we have a second derivative here, right? But after we applied our integration by parts, now our highest derivative is 1. It's just we split it up into 2 terms. And so it's a little bit hard to kind of see why that's nice right now. But once we go through Wednesday, and then once we see how this is applied in finite elements next week, you'll see that having only a first derivative is extremely nice for finite elements, and it makes our lives actually significantly easier. So that W of X right there is really meant to kind of just take the total order of the equation down by 1. Yeah. Mm-hmm.
Professor?
Yep.
I have a quick question. So the ANSYS assignment, is it due on Sunday or this Wednesday?
So the ANSYS is due this Wednesday. Yep.
Okay.
Yeah, Wednesday at 11:59 p.m.
Thank you.
Yep.
Professor, I have a question regarding problem number 7 for the homework.
Okay, sure.
When I modified the MATLAB code, but I'm getting like an error that reads index in position 1 is invalid. array indices must be positive integers or logical values?
Okay. Yeah, probably for any MATLAB issues, I think probably be easier to for you to send me the code, and then I can look at it. That's usually the easiest way, because it's a little bit hard to kind of debug MATLAB code just by talking like this. So that error that you just described is something that can happen pretty common in several areas of the code. So if you send me your MATLAB code, then I can take a look, and I can you know, send you my thoughts on it and help you debug it.
Okay, I'll do that. Thank you.
Yep. Mm-hmm. Oh, did I say that?
Yeah, you said that.
Yes.
Okay. Okay. If everyone's saying I said that, then I said it. So it's gonna. So that will be reality then. So the homework will be, the activity will be due Sunday at 11:59. Yes, the 18th.
Thank you.
Yeah. Sorry about that. It must have just totally slipped my mind from last week. I think I remember now, because you know, we had the midterm, and this activity is pretty lengthy in how much I'm asking you to do. So yeah, I remember that now. So it's pushed back to the 18th. Yeah, thanks for reminding me. I totally forgot. So I'll update that on the Canvas. So it'll be due on the 18th, guys.
Thank you.
Yeah. Yeah, I'll send an announcement for that too.